Perfect. That is what we're looking for. That is change.
I forgot how you plug it into the calculator.
Hopefully the next 20 minutes of me talking about it. That's what we're going to start with. That's going to give everybody a break. We all have our TI 30 XAs, right? Yeah. We're going to turn them on, and the first thing we're always going to do is make sure above that 0 it says DEG. If it says anything else, let me know.
It says God.
Thank you. That's one of the ones I was looking for. Does anyone else to say anything besides DEG? All right. What does yours say, Bree? I've never seen it say, I don't know.
Oh, I was looking here.
Oh, I'm sorry. Yeah, on your display, right above the 0. Wrong. Yeah, that's the cube root. That would make it really confusing. So on your display above the 0, DEG. If it doesn't say that, there's a button next to second, DRG. Press that, and it'll change it. And then press it one more time, sir.
DEG.
All right, everyone that's in DEG, go ahead and hit it so it's in radians. So you have that budding muscle memory of how to get it back in case you turn it on during the EOC and the guy or lady before you decided to mess with you by putting it in radians. So everyone can cycle through those 3 options, right? We're good? In geometry, we are only working in degrees, never anything else. Most of the time when students say, I did everything you said to do, I got a different answer. First thing I look at is it in radians. If it's in radians, we do it again, we get the same answer. Make sure I'm recording. Yeah. All right. So, the cosine, the sine, and the tangent of A are represented by these ratios or fractions. But what I want to do is I want to find out, I'm going to write this, we'll start with sine A. And basically what I'm reading here is the sine of reference angle A is 4/5. And we know the inside of a triangle has to add up to 180. So we're going to ask, when we have an opposite that's 4 with a hypotenuse that's 5, what angle generates those two segments? And to do that, think about it this way. If I have 3x equals 12, how do I undo 3 times x? Divide by 3, right? And that pulls out what x is. I told you how to find, or how to undo sine of reference A, and that's doing this right here. Alright, well, I guess technically we can put it all the way to here. So basically what this saying is, some unknown angle generated an opposite side length of 4 with a hypotenuse of 5. Because this is a right triangle, we could find that the other side 3, but we don't care about that. We're asking, what is that angle? Well, to get rid of the signs, I have to undo them. So I'm going to put in my calculator. 4 divided by, if you see a box around it, that's a physical button you're going to press. Everything else is just a number that should be on your display. 4 divided by 5 equals second sine. Now, because I had reference angle A, and I found the sine of it, and then I found the inverse sine of that, that just tells me that the measure of angle A is, I'm going to round to the nearest tenth, 53.1. Did anyone get something different? Did anyone not get there yet? Evan?
I have everything, but what is the 3x over 3 equals 12?
Sorry, that was just to show that back in Algebra 1, if I gave you this, you would know the opposite of multiplication was division. And I just wanted to draw a parallel that the opposite of sine is inverse sine, just to kind of prime that connection. So that was just pulled out of thin air so we could talk about opposites. All right. So did anyone get something different than 53.1? Okay, let's make a prediction. And we gotta talk about the fact that what we're doing here is finding, even though it's on the board of projections, this would be a real triangle, right? 3, 4, 5 makes a real right triangle. If finding sine of A in 4/5, and then I did the inverse sine to get angle A, and I got 53.1 degrees, without using your calculator, what should the inverse cosine of 3/5 be? It's still going to find angle A, so I should get the same answer for both cosine of A and tangent A. This is why we call this our reference angle. It should be the same for all three trig functions. We need three different trig functions because we may not have all three sides like we were unfortunately given this time. So go ahead and punch in cosine of A. If you get 53.1, set your calculator down. If you don't get 53.1, try again, raise your hand, call me over. When I see everyone's calculator down, we'll talk about it. Sydney.
I'm doing the signs of C or something.
No, we're going to stick with A. We're going to show that all three of these get the same answer. And just do the cosine of A now before you set your calculator down. Got the same thing for you?
This is wrong.
Say it again, sir?
Trey, Mike, right?
Are you working on this already?
Yeah, I thought we
Did you already do these two?
over 2.
Yeah, let's prove that the sine of A, the cosine of A, and the tangent of A produces the same angle every time. If it doesn't, we've made a mistake because we know this is 90. We know these side lengths have to connect to make an angle. And we want to show that no matter how we use it, our reference angle A is always going to be 53.1 degrees, whether it's cosine.
You get it 0.0232.
Second tangent.
Oh, second.
Or second cosine, then second tangent. Yep. All right. So that's what I was going to ask. Did you do second or just regular cosine? Anytime you have the angle, make sure you hit second. Varun, did you get 53.1 for cosine of A?
Oh, it's getting here.
All right, that's a good thing. Maybe let's see what we can talk about. I see your screen. So show me how you put it into. Go ahead. Yep. So the calculator is not as smart as you, but it wants you to do 4 that 3. Oh, you did 4 3. Look at this. 4 3 is tangent.
Oh,
Yeah. So do 4 3 and then set. Try it your way. I want to see if it works. Second tangent.
okay.
Hey, Varun found something I like even better. He's putting it in using the ABC option. He put 4 ABC bracket, second tan. Oh, I'm in radians now. 4 ABC, second tan, and you got 53. Boom. Did anyone not get 53.1 here? All right, let's try and make a prediction here. If this is 53.1 and this is 90, without doing any of this, what do you think this will be approximately? Let's do a prediction. C should approximately be, how do we do that right now? Not an exact answer. We know 2 of the 3 angles. How do we find that third one before we learn trigonometry? Perfect. 180 minus 90 is 90. Minus 53.1 is 26.9? Thank you. So we're going to say this should be about 36.9. let's get an exact answer here. Do the same thing here. 3 divided by 5, or like Varun did, which I like a lot more right now. 3, ABC 5, second sign. And that's going to pull the C out and tell us exactly what it should be. Is your answer on your display for any of these three very close to this? And now we're looking straight into the face of the difference between an exact answer and an approximation.
I did cos A and I did the same thing.
Now, really quick, let's look at something here. The cosine of A has the exact same setup as the sine of C. And that's just because we're swapping the relationship, right? So if I know that the sine of A is 4 over 5, without even looking over here, the cosine should be 4 over 5. And when you swap the angles, sine and cosine swap their side. We'll do that forever in pre-calc. I just want to show you that. So if you ever want to double check your work, they should be in that fashion. And then look here, these are just the reciprocal of each other. If I change my reference, it reciprocates my tangent. Now, pre-calc, there's 3 more trig functions you haven't heard of yet, or you've read ahead, or you took algebra 2 and your teacher showed it. I don't know. But there's 3 more, and they cover all the bases at once. I'm just giving you a heads up that this will happen. Now, our precise answer, our more precise answer, is 36.86989765. Right?
That's what I got. 36.
So, you can represent this as inverse sine of 4/5, inverse cosine of 4/5 for precise answers, or this approximation if I say around 10 nearest 10, this approximation if I say it's around here and it's less than 4. But that is everything you need to know to set these up for the EOC. If it asks you for an angle measure, it's second in your trig function. Take a minute. I've got a couple people staring at the floor. Not that there's anything wrong with it, but I'm giving you the minute for that brain break. Any questions? Anybody need a minute to catch up on all of this? Anybody want to do one more practice problem?
Let's do practice.
All right. Ruben, I'll draw one for you.
Huh?
I'm going to draw one for you, sir. Let's call this angle V. Let's say this is what is the measure of angle V? So first, my question is, what's our reference angle?
Reference angle is.
What does it mean to be a reference angle? That's where we base all of our decisions off of, right?
Yeah.
If I'm asking for angle V, what does that mean? It's my reference angle, right?
Yeah.
So if I look at V, what's the relationship to 4?
It's 4 out of 8, right? 4 under 8. 4 fraction
4, 8 like this?
8. Yeah.
Okay, we could do that, but which trig function is that?
That's gonna be a tan.
Man, really weird, yeah.
And
What is the measure of that angle, sir?
using inverse?
Yes, because we're asking you for an angle. Angle, not anger. Abby,
It's 26.5.
go ahead.
What if the problem gives you all the sides of the triangle? Can you just choose whichever one you want? Sound kind of something?
Yeah, like here where I gave you all 3? Yeah, you're absolutely allowed. Now, I could arbitrarily assign something here, but that's dangerous. I would need to use the Pythagorean theorem. It should be 1664. Yeah, if you had this, you can use any one you want.
Wouldn't it be 26.56505?
Varun, is that what you got?
Yeah.
Then yes. I didn't do it on the calculator, and there's no way I'm doing that in my head, so.
Wouldn't it round up to 26.6? Because
Yeah,
that's
you can do that.
5/6. Just making
Yeah. You're good. So, Did I do this right? Like 64 and 16 is 80, right? So, using V for my reference angle, let's do the sine of B just to get this scary idea out of our head. The sine is opposite, which is 4, over hypotenuse. How do we put that in the calculator? This is why I really quick want to address it since it was asked anyways. Hey, you can see the board here. Alright, here's where most people make their mistakes on a question like this. It's putting, where do I put the radical in? Before, after, during? Can't really do during.
After, right?
Let's see. So we would hit 4. We've cleared the numerator. Next is divided by. Now, Varun said after, so what I'm hearing you say, sir, is punch in 80 and then the square root? Is that what you said?
No, I think you put it in the thing.
But I can't do that in the calculator for this one. I'm saying on the calculator, I'm going to hit 4 divided by, and then do I hit 80 square root or square root 80?
Square root. Square root.
I heard 80 square root?
Yeah.
80 square root, anybody have, yeah. It's going to be 80, then square root, then equals, and then second sine. And what does that give me? The same exact answer. So this works, and that's why this all works. This is why we make you learn all 3, in case you only have 2 of the sides. And then if you want to check yourself, we can do like Abby said, and what if we could find the third side before we use that? Absolutely, and I think that is the best way to walk out of that room confident. If you have 30 minutes left over, you've checked all your marked answers, and you want to do something like this, just to not only pass the time so you're not sitting there doing nothing, but feeling better about it, I encourage that. Feel good? Alright. What are we at next? Alright. Dilation. Alright, so what we're going to be talking about now basically is there a scale factor or a number that I can multiply each side of this projection here? We use this white box, so this and this are going to be congruent. We'll say this and this are congruent. Is there a way that I can take this white box defined by these congruency marks and multiply each side by a number that'll map it to be exactly the size of my board? For this, probably not, but we're going to talk in very general terms. Is there a number that this square of side 2 can be multiplied by so that all the side lengths become 3? And I chose 3 because everyone was nodding so confidently, and I think if we don't get a whole number, we might have a moment of panic. 3 over 2? Yeah, 3 over 2. 1.5. I'm trying my best. I promise I'm the signing. I have to ask myself, 2 times what number? 2 times some number, the scale factor, is equal to 3. And if I can find that, then these are what we call similar. And the notation for that is the congruent or approximation, but only one of those. So what is n going to be equal to, guys? Divided by 2, and we have 3 halves. Easiest case, right? Because all 4 sides of the one on the left are 2, all the 4 sides on the right are 3. If I multiply these by 3, 2, I get 6 over 2, simplifies to 3. So here, when we write it, to do this properly, I'm going to tell you to dilate, and here I have to know where I started versus where I ended up. Dilate by 2. Now, I'm not putting a point here. It's not on a coordinate plane, so it doesn't matter. Right now I'm just telling you indiscriminately double the side lengths from small to large. Alright. I'm not doubling it, I'm doing it 1.5. Alright. Now, it gets a bit more complicated if we don't have a regular polygon. Remember that a regular polygon has all the same side lengths and angle measures. But I'm going to let you guys catch up with this. Actually, before we do that, if n is greater than 1, it's going to get larger. If n is less than 1, it's going to get smaller. And if n is equal to 1, it stays the same. So when we talk about congruency, our scale factor is 1, it stays the same. The difference between similarity and congruency. Similarity, the angles all stay the same. They don't change when I multiply. And every side length grows by this scale factor n. Angles stay the same, right? If I were able to blow my projection up to map exactly onto the whiteboard, they would still have 90 degrees in every corner. There would just be a scale factor from each part to the next part. So here, I have a dilation of 3. Is that going to get larger or smaller? D3. The question becomes, is 3 greater than, less than, or equal to 1? If it's greater than, then the shape that it results in is going to be greater than in length than the other. So it's going to get larger. Here I have 1/5. Is that less than, equal to, or greater than 1? It's definitely less than. It's 0.2. So is this going to get larger, smaller, or stay the same? Perfect. Here I have 1.2. Larger, smaller, stay the same? Definitely larger. 1.2 is greater than 1. If you're ever questioning it, would you rather earn $1.20 per hour to be at tutoring or $1 per hour to be at tutoring? Right? It's a better deal to get $1.20, so it's going to get larger. Your paycheck will grow. How about this guy right here? I just have D6. Smaller, larger, stay the same? By how much? 6 times as much. Yep. And last one. Here I have dilate by 1. Smaller, larger, stay the same? Perfect. So let's see if we can prove whether some things are similar or not. Couple things. Let's start on an easier setup. Which of these triangles was my original? The one on the left or the one on the right? Why the one on the left? Perfect. The one on the right, just say that again? Okay, I heard you right, and then I was like, back up, I'm going to say it right, but then I realized I actually didn't listen, so I'm sorry. So yeah, A to A prime means this is my start. This is called the pre-image. A prime means I'm going from this one to this one, and this is just called my image. So, let's say, well, here's something else that's extremely important. When I'm looking for similarity or congruence, we'll get to congruence in a little bit. I want to make sure that these are either already orientated in the same way, which here they are. A is in the same place as A on the triangle, B is the same, C and C are in the same place. If they're not, I need to see if there's a way I can flip them, map them back into this orientation. Because, well, we'll get to that in a minute, but let's do this one first. Let's say this is 1, this is 2, this is 3. Let's say that this becomes 6, 12, 18. My question then would become 1. Are they similar? Well, AC, the length of AC was 1. The length of AC, A prime, C prime is 6. CB is 2. C prime, B prime is 12. And AB is 3. So is A prime, B prime 18. Do I need to multiply 1 by the same number to get to 6? Do I need to multiply 2 by to get to 12? and 3 by it to get to 18.
Well, that's 6.
It is 6, yep. Now, how do we check? We're going to do the image divided by the pre-image. That just means I take whatever this is and divide it by whatever it started by. Gives me 6. Here I get 12 divided by 2. That is 6. And 18 divided by 3. These are my scale factors. And since they're the same number, these are, in fact, similar triangles. That means their angles are preserved. All of these, angle A and A prime are equal. B and B prime are congruent. C prime and C are congruent. But the side lengths have changed. Similarity preserves the angles. They stay the same, but the side lengths change. All right?
So basically you're just trying to find what is the same, what is different, and what is less between these two things.
Yeah, the easiest way to break this down is, can I multiply each of these numbers by the same number to turn them into their new number?
Oh.
That's it. If you think of it that way, can each of these both be multiplied by the same number to get that new number? If it's always the same number, you're good to go. Let me show you when it doesn't work, but before I do, does anyone have questions? Abby?
On the bottom example, just the center of dilation,
Yes.
the squares at the top don't have none, right?
Correct, yeah. So what you're seeing here, what you're asking here is basically why did I not include this or a specific place to dilate from, right?
Or what would it be?
There isn't one in this case because I'm just asking you to multiply the sides. I could say at D, if it's on a coordinate plane, and let me just show you really quickly. This thing's broken. Oh, jeez. It never stays down. So, here, let's say that this is DC, right? I can see that that's 1, 2, 3 units. If I were to come here and make this D prime, and this is, let's see, 1, 2, C prime. This is 1, 2, 3, 4, 5, 6. This would be the dilation by 2 from point D. That means we're starting here and everything's pushing in the direction away from D. If I wanted to go up, if I went up 2 here, that means I only go up 1 here, right? This preserves, this length is 1, this length is 2. It's still twice as far, but I drew that upside down. No, it has to go that way, yeah, from D up. If I drew D down, then it would go down too. Because it's C, or D is where everything goes away from.
Wait, so basically it's like, if this, I'm so confused, like basically if one area thing goes up, the other thing goes up.
They travel in the same direction, yeah. If your pre-image is moving up away from D, your image is going to move up away.
Wait, dilations are basically we write like it's like notations in the graph.
Huh?
I think in like topic 2 or 3, where there was like reflection, translations,
That's 4, yeah.
transformations. You said you didn't want us to do dilations until like topic 7.
Yep.
Oh,
We're on topic 7.
Oh.
And we're going to go second. Is there a question on this or over there?
On that, so does the center affect calculation?
Yes. And let me change fingers before I lose this one. So what's happening when I dilate away from D, right, is this has to be, well, this is going to end up being here. Way more advanced. This is something you do in pre-calc with triangles. All of these on the outside dilate at the same rate, right?
Mm-hmm.
Right, double, 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 double. Is it always true that the diagonals double at the same rate?
Yeah.
Can you prove that? But not today?
I don't know.
Write that down as a bonus question. If anyone can show me that the diagonals are also scalable by the same scale factor, I'll give you bonus points. If they're not, and you have a proof on why they're not, I'll give you bonus points. I'm not saying it has to be right or wrong.
Wait, these two things?
Yeah, I'm just saying that if everything on the outside dilates at the same rate, right? The scale factor here is 2. Does that mean the distance from D to here is scalable to the distance from here to here?
No, I'll tell you why.
Why?
No, mind.
Root 2 is
Wait,
1.
so wait, go back. So, this one is like, because you said that like one free image moves, the other one moves. And if
Proportionally, yep.
If this one moves, the other one will move, so it won't be like perfectly the same.
So what I'm hearing is a proof of concept. Can you turn that into a proof for bonus?
What do you mean?
When you go home today and next week and the week after, I'll give you 2 weeks to answer. Can you show me that these diagonals grow at the same rate that the side?
No, they can't.
Why can't they? That's what I'm asking. Devin?
I really like points, so I don't know if this is right or wrong, but if we wanted to find the distance of that diagonal, the first one we have to do 3 minus 0 plus 1 minus 0.
Yes.
Square and then square both of them and then do the square root of those added together. And then if we take the second one, we'll do the same thing essentially, but both of the numbers would be doubled. So because both of those numbers are doubled, the diagonal would also be doubled and the scale would be the same.
That's your whole proof. If you guys wrote that down, turn it in. Yes, that's it. Now, Devin, when you turn yours in, say I actually did the work and everyone else copied me, I'll give you a little bit more. Okay? But yeah, that's exactly what happened. You would take the link here and you would show that the same scale factor applies there. And it makes sense. I don't know if this is going to blow up in my face. It probably will. It's at least going to make my hands disgusting. These are supposed to be pretty stretchable, right? Now, I promise we didn't go get candy so I could talk about math with it. The length of this is set in stone. We're going to imagine it's a perfect polygon. So from this corner to this corner is the diagonal, right? If I stretch it, it's working. There's definitely a scale factor that'll take the original to this size, right? Oh, I put a hole in it. Now, from this corner to this corner, that diagonal also had to grow proportionally, right? And that's exactly what Devin's showing you. Oops. All right. So, I'm not going to offer anyone the chance to eat this. It's gross. Shame.
So for extra credit, can I just say I agree with Devin and move on?
I agree with Devin, and I can paraphrase Devin, yes. Give me at least someone, like, you can say I agree, but why do you agree?
Because he's smart. I didn't chew either. You took it out.
Do you really want to watch me for 3 minutes chew through a Snapchat? Airhead instead of,
Don't take it out.
You know, it's even like,
what if we do this? I'll say when you guys all leave, I'll come back and eat it, then when you feel better.
No.
Because you don't have to see it.
Then I need to go back.
Okay, can we make a meat in the middle? I'll take it out. Wait, no. Let me finish it. I'll take it out and I'll feed it to ants.
No. Okay,
Then it doesn't go to waste.
Let's go on.
Please wear gloves.
For that trash can, did anybody even use it? Oh, yeah.
I've been dying. Wait.
Okay.
Oh,
Alright, let me figure out how to make the world right with that mistake. But while I do that, let me set up this problem for you guys. Broom, are we only on like 15 or 50? You better speed up.
what? It's 52.
Huh?
It's 52.
No, not here. We're only on slide 15 out of 50.
52?
Yeah, I hope you guys are ready to stay till about 6. Alright, real quick.
Oh, that makes sense.
Who was this sarcastically?
Why did everything in math have to revolve against the Pythagorean theorem?
Say that again, sir?
Why does everything have to be with the Pythagorean theorem?
Why there's so much junk? I don't know. It gives its founded, its base. So, right now, are these two orientated in a way that I could start answering this question? No, right? I mean, if you want to look like a lunatic. What I'm going to do then is I'm going to, in my mind, rotate this 90 degrees so that C comes to the top. If C comes to the top, B comes down here, A comes over here. Now, are these set up the same so that I could make a corresponding judgment on whether or not there's a scale factor? Right? So let's call this prime. Boom. So, are these set up the same now? Orientation-wise, I know they don't look anything alike. These are fraternal twins at force.
Well, then, are you comparing it to the original, when you look at it?
Wonderful question.
CBA, or are you priming it? Because you also put primes on CBA.
Correct.
So is that two prime?
Great
So
question.
it's a,
Let me restate the question. First question was, should this be C double prime, B double prime, A double prime, right? And I'm going to say no, only because I'm not actually doing, like, I need to prove these two are the same. This is just a visual aid so that I know they're orientated the same. If I go to do this, let's say I put here 2, 6, 9, I go 16, 48, 72. That doesn't work, does it? That is definitely not similar because BC went from 6 to 16. This is how you thimble a problem like this, right? It's not orientated right. I look at this and I go, wow, times 8, times 8, times 8, yes. And I move on and then I realize I got that wrong as soon as I hit submit on the test. So, if it asked you to orientate them in the question, then you would do it. I'm only rewriting this for my benefit, but I still have to make my final judgment off of this. So, if the directions explicitly said rotate this to here, then you would increase the prime. What this is doing is preventing me from having to do stuff like this the whole time. During the EOC, I think it's easier to redraw your triangle than to pick up the monitor and turn it. Because if you pick up the monitor and start rotating it, what's the proctor going to do?
Kick you out.
Well, first they're going to go, are you okay? Right? And then, when Brune says yes, they're going to go, I don't know about that. Let me talk to Miss Platwell. And then, yes, they'll probably remove you, let you see the nurse. Or they'll ask you to stop, and if you do it again. So, we're not going to increase the notation. We're just reorientating it for ourselves. Now, I can say, if this goes 16, this goes 48, and this goes 72, I can do my comparison here. On the left-hand side, 2 times 8 is 16.
Wait, I have a question.
Yeah?
Wait, and like, what happens if it's all false? What will you say as your answer?
If they all what?
If they don't work, what will you say for your answer?
Not similar.
Not similar?
Yep, that's it.
It'd be like similar or not similar?
I guess, non means not, right?
Yeah.
is there a symbol for not similar?
Yeah.
I'll tell you a secret in math. If this means similar, this means not similar.
Oh, it looks like a...
Now, it's easier to just know that they're not, you know what I mean? Similar is stating a claim that you need to support. I don't think we would always need to say not similar. Is 6 times 8 48? Is 9 times 8 72?
Yeah.
These are similar.
That's it?
Those are similar, yeah. That's it. All right.
Topic 7 is like the fourth biggest, right?
Yep, they're all in order, yep.
Oh.
Let's say that I have 1, 1, 2.
Okay, I think I'm in the class.
Are these similar? Paulo, why are these not similar?
Oh, yeah, that's not
Perfect. To go from here to here is 1 times 1, but to go from here is 1 times 2, and then here to here is 1/2. These are not a triplicate of the same number. This is not similar. Vern, you see the difference? Here,
Yeah.
I would say these are not similar.
Because you changed the thing.
Yep.
And then, yeah.
I need 3 in a row. I would say
Bingo.
like bingo, but that's not how bingo works. Tic-tac-toe. All right?
Okay, now we go to skill factor, right?
We did all of that. But now, well, this is what we've been doing, right? Let's try and do it on a graph. So much of geometry has nothing to do with a graph. So we're going to do some of our graphs.
Oh wait, and then graphics is basically the same thing.
Say it again, sir?
And then graphics is kind of the same thing, right?
It is exactly the same thing. I think it's easier. They didn't give me numbers, but Varun, what's the length of AB?
A and B is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
This is A prime, B prime. How about this thing? This right here.
No, 1, 2, 3.
Now what is A prime, B prime?
I mean, it's 5 because
So here, 1, 2, 3,
1, 0, 1, 1.
9. It's okay, it's been a long day already and we've got 2 more hours. Now, what's my scale factor here?
Scale factor is 6, right?
To do that, I take the image, divide it by the pre-image.
Oh, wait, that's
It's 3, yes sir. Now, what is BC?
BC is 1, 2, 3, 4, 5, 6, 7, 8.
8. Wait, is that B prime, C prime?
Oh wait, no, that's a small one. That's 4.
So from here to here?
Yeah, that's 4.
Double check it for me.
Yeah, 1, 2, 3, 4.
Ah, I see what we're doing. He's starting here. We only want to worry about the length of BC itself, the line.
Yeah, 1, 2. Oh wait, 2.
2, okay, yeah, you're kind of, yeah. So it starts here, ends here, 2.
Oh.
It's okay, man. You just said confidently you're ready. And then... Now, let me ask you this one. Don't count these. If these are similar, what does the length of B prime, C prime have to be? To go from 2 times 3 is
6.
Is it 6?
I don't know.
Let's find out.
1, 2, 3, 4, 5, 6, 7.
So, the scale factor here is 6 divided by 2. That gives me 3. I'm going to get a drink of water. You guys do CD, C prime, D prime. See if they have the same scale factor.
Well, it's the same thing because B and A and C and D is the same.
Varun, you took my next point. I'm going to give you that aha moment. But did you hear what Varun said? It's on a graph.
It's a rectangle.
It's a rectangle. We can see those lines are perpendicular because the vertical lines have an undefined slope and the other lines have a 0 slope. Anytime a 0 slope and undefined meet, what do you get? Perpendicular lines. It's a quadrilateral with 4 90-degree angles, varying side lengths, but those lines are parallel, so those are congruent on each side. Watch the board, I almost try to drink you a mask.
I mean, what was the 2 more things topic 3?
Huh?
Then we do topic 3 and then
Yeah.
topic 1. Oh, topic 1's easy.
I think, oh, does it say 1? That should say 12.
So 3? Oh, wait, 12.
Yeah, we'll figure it out. Second.
On the A to C, will we need to know things like converses, contrapositives,
Yes.
and properties?
Yes.
Oh,
We'll,
all circles are similar. Wait, what do you mean that all circles are similar?
I promise you I'm going to show you that next. But let me ask you guys this.
Oh, like all circles equal 360. No.
Sort of. Do these all have a scale factor of 3?
Yeah.
Verifiable? Okay. Now, the next slide says all circles are similar.
Which is true.
Can we do, again, I know this is going on YouTube, so I don't want to use the word truth because it wouldn't be. Whoa, wrong direction. Let me show you this idea. No, I don't want to show you this idea. So, I'm going to do it, but I'm not going to use, let's say that I have a square with side length 2.
Okay.
Then I have a square with side length 4.
Wait, I have a question.
Yes.
Okay, I'm just curious. It says square and parallelogram.
Yes.
Oh,
Yep. Remember, square is the most specific. Everything that comes before a square in that regard is true.
oh.
Are these two shapes similar?
No.
Why not?
Because that one's bigger and the other one is small.
Did I say similar or congruent?
Oh wait, congruent. It's congruent.
No, they're similar.
Yeah, they're similar, but and also they're congruent.
Congruent means, and I'll show you that next. Congruent means same side length and angles. Similar just means same angles, different side lengths with a scale factor. All the sides of this one are 2. All the sides of this one are 4. So 2 times 2 is 4. My scale factor is 2. Right?
Yeah.
If I inscribe a circle in both of these, well, we're going to pretend it touched.
That's a, how do you say, that's a sector, right? I don't remember.
Inscribe. This is just called an inscribe circle. It just means it touches, each of these are points of tangency. They only touch
Yeah,
there.
that's like, what is that word that's, how do you say it? It's like it's like a,
Are you talking about these lines here?
yeah.
These would be tangent lines.
No, the one that's touching you, there's some word that.
Points of tangency.
So you said there's a line that connects, that touches that line you want.
This is the, oh, yeah, what I said is if we had a line like this, that we push to the extreme where instead of touching twice, only touch once, this is a tangent line. This was a secant up here, but we're not going to do secants right now.
Oh, yeah, so that's what it is.
Secant's the one that you seem to gravitate towards. I have a question for you guys. What's the radius here? And what's the radius here?
How do you know what the radius is?
That's a great question. How do you know what the radius is?
Oh wait, 1.
Why is it 1?
Because the whole big length.
Yeah, the diameter is 2.
Yeah, and the radius is 1.
So the radius is 1. What about here?
The radius is 2.
Okay. What's the scale factor to go on the square from 2 to 4?
2.
What's the scale factor on the circle to go from 2 diameter to 4 diameter? 2.
2.
What's the scale factor to go from the radius to the radius?
1.
2. 1 times 2. Right? All 3 of these show that they have to scale up the same.
Yeah.
So what I'm going to ask is, if I bring this down to be 3, 3, 3, 3, wouldn't the circle go down by the same amount?
Thanks.
Oh, what's the diameter? 3.
3.
What's the radius? 1.5, right?
Oh, yes.
Okay. Now, I'm doing this with squares. Is there a way that I can inscribe a circle in a rectangle? It's a little tricky, isn't it? But think about that. A circle has constant width in every direction. If this is 4 and this is 3, if I do this, it's not going to cut it over here, right? There's too much room. Now, my question is my rectangle and my square here similar? Well, 2 times 2 gives me 4.
Oh, yeah, 2 times 2.
But does 2 times same scale factor? No, right? Do I have a different scale factor? What's 4 divided by 2?
That's 2.
What's 3 divided by 2?
3 divided by 2 is, I think, 1.5.
These are not equal, right?
No.
These have different scale factors. But I'm still bound by the definition of a circle for these to be 1.5. Right?
Yeah.
So a circle can only be drawn inside of similar shapes. So if it's a non-similar shape, I can't fit a circle in it. This works for triangles, this works for everything.
Yeah.
A little deep, I guess.
Yeah, I got it.
But if you think about what a circle is just by definition, a circle with 0 radius is a point. And no matter what, how large it gets, I can always draw a box around it that'll be similar to every other box I draw around it. If I can't inscribe the circle into this box, if I don't, it's not going to be similar. That's just basically what similarity is. Abby, go ahead.
Can you repeat the definitions for similar and congruent?
Yeah, definitely. We're going to call them similarity and congruency transformations, since we're coming up to that. Similarity preserves angles, changes sides by a scale factor. Right? So here, just like we have squares, side 1. We had a square, side 2. The angles are preserved as it gets larger, but the side lengths have changed with a scale factor of 2. And now I want to show you something here. Similarity, this symbol basically means the angles are preserved. Alright? Now, let's change colors. For congruence, let's look at what that symbol looks like. Congruence is preserves side lengths and angles.
What's the difference between that and
Say it again?
what's the difference between that and it's the same number?
That's actually what I want to show you, because the congruence symbol is a marriage of equals and similarity. I'm going to show you why in just a second. Now, Abby is taking my words right out of my mouth, and this is what I meant by it's going to get faster as we go, because you guys are asking all the good questions. Abby's question was, then how is this different than equals? When we use equals here, if we're talking about lines, like, for example, the length of AB is equal to the length of AC. To show that, right, that's just equal. Does that make sense? But equals is just showing that the lengths, the measurable lengths are the same. Equals says nothing about an angle, right? Similarity saves the angles and changes the side lengths, right? So if you think of equals as side lengths, you think of similarity as angle measure. When you put these together, you have to preserve both the side length and the angle measure. And that's why that symbol looks like it does. It's both of them together. This is the angle part, and this is the side length part. And just like someone asked, was it Varun, would you write not similar? And I just put the strike through it. It's the same thing. You can put these symbols together in meaningful ways. Shane.
The numbers that you've been like putting around the perimeter of the shapes,
Yes.
those are the side lengths.
Yes.
So why were you trying to prove those to be the same as?
I'm proving that it takes the same number, like this times the same number to get the side lengths.
Okay.
And then I'm just using these to show that instead of writing 1 3 more times and 2 3 more times, I do the same.
Okay.
That was a good question. So, it was Abby that asked, does that kind of make sense? When we talk about length, strictly length with no angle measurement or preservation, we use equals. If we're only talking about preserving angles but not worrying about the side lengths, we're going to talk about similarity. And then we put those together to say we must preserve both the angles and side lengths. So, the other way that you can show that all circles are similar.
Isn't there like a theorem about it?
Yeah.
What? I forgot. It looks like this theorem saying like, I forgot.
Well, let's show. I'm going to erase this really quick. I'm going to leave this up over here. Okay. Let me put this in my mind first.
That's the radius.
That is the radius. Perfect. Notice again, you don't trust your eyes. This one's definitely larger, but it looks smaller. All right. How do I find the circumference of this one over here?
You have to circumference 2 pi r, right? And
How
that's
do I do it over here?
2 pi r. And then it would be 3, it's the radius. Then times by 2, with 6 pi.
Perfect. Now, I'm gonna ask you this question. And gets a little weird. I'm gonna add a variable here. This is my scale factor, right?
Yeah.
I want to know, is there a scale factor between these based on the circumference? Does that make sense?
Yeah.
So, well, this is going to be 2 times pi times 3. N is equal to 2 times pi times 2 n. Can we agree on that?
Yes.
Let's do some simplification here. I'm going to divide by 2. I'm going to divide by pi. I get 3n is equal to 2. Let's not put the n here. Let's make it easier on us. This is just asking, is there a number that I can multiply this by that'll result in this? Does that make sense? That's what the scale factor is. It's that number, what I have to multiply 3 by to get to 2. Then, this is going to tell me that n is equal to 2/3. Is n equal to 2/3 here?
Yeah.
So all circles are similar, right? It just tells me, well, let me do this. If n equals 2/3, I would need to multiply this by 2/3 and get this for it to be right. Is that correct?
Yeah.
3 times the scale factor gives me 6/3, which is 2. So for every circle, if I say the circumference times some scale factor, has to give me the other circle's circumference. And I can show it that way, I'm good to go. And that's why all circles are similar. Based on visuals, by trying to draw it into those quadrilaterals, and based on just the math behind it there.
Yes.
Now, is any of this really necessary? No, but now do I feel like you, or, well, you, I don't want to speak for you. Do you guys feel like you have a better understanding of why all circles are similar instead of just taking my word for it?
I got it.
Whether it's drawing it inside the squares or trying to do it this way.
Yeah.
I guess the fastest way to write it is the circumference times the scale factor is equal to the circumference, right? That's exactly what I have here. Expand circumference to be 2 pi r times n. And then we can do all these steps and we'll get our scale factor to fall out from there.
Well, I'll talk 3 next.
Are we already there? 3, do you need to go the other way?
What time is it? Oh.
Way over there.
I have a question. Yes.
Alright, any questions before we move on? I think it's easier to see here after the fact than if you don't follow.
Yeah. Got it.
Alright. Now we're going to talk about rigid motions. Now this is backwards from the way we learned them during the year. But when it's review time, I'd rather stimulate the harder stuff first and then come back and talk about what's going on here. So now we're moving from similarity to congruence, which means we must preserve angles and the side lengths must be equal, and that's what that means. And Abby beat me to it, but unlike a dilation that preserves angle measure but scales the sides by a set ratio, a rigid motion is a movement that preserves angle measure and side length. The translation, who wants to volunteer?
but I guess.
Alright, come on up. Varun, you were quickly becoming my favorite person in person. Never seen someone move their desk instead of their chair.
Yes.
Varun, don't trip on letters. Start right here, man.
Yeah.
I'm gonna ask you a question. The translation is just moving something without changing its orientation. So Varun, I want you to translate 3 steps towards me.
We walk
1, 2, 3. He took 3 steps in this direction. Is he facing any other direction? Did he rotate at all? Did it reflect at all? No. Translation is preserving everything, it's just moving. When I said Varun get up, he translated his desk forward. Right? Everyone else translates their chair backwards. Varun's rotating right now, but we're not ready for that.
Oh.
Varun, what I need you to do is reflect over yourself. Which,
Oh wait, meaning you have to go back.
let's do this. Varun, stand right there and look straight into the camera.
Oh yeah,
No,
right.
that's production. The camera's on there. Get a little bit centered up. Make it look professional. Okay.
I look professional.
Huh?
I look professional.
You do, and then when you're in frame, you look super professional. Now, I need you to reflect. What would it look like if you were looking in the mirror?
Where's the mirror?
There is no mirror.
Oh.
But, so this is a tough one to do in person.
Yeah.
Let's say that this is the mirror.
Yeah, I can see it.
If you reflect over it, right, you'll be the same distance away from my hand, but on the other side. So go to the other side of my hand this far.
I guess so.
Now, which way would you be facing though?
Oh, I'll be facing this way.
In your reflection?
No.
Can you imagine going to brush your teeth and you see the back of your head? There we go. Now it is. So that's what a reflection is. You're faced this way, then you face the opposite, right? Your reflection turns it over. Varun, before you sit down, can you rotate 360 degrees?
1.
That's it, right there. One full circle, right?
Yeah.
So if I said 720, how many times would you spin around?
Wait, what? Oh, that means 2 times.
1080?
That's 360 times 2 is 720.
Yes, sir. How about 1080 degrees?
1080?
1. Yep. 2.
And that's it.
I promise I won't do any more. Yeah. 3 turns and you're done. Do you feel safe to go back to your seat?
Yes.
Okay, but wait. To go back to your seat, I want you to reflect the whole way there. Every step has to be a reflection.
Reflecting, that's translated, right?
Yeah, just walking normal is translated.
Oh,
What
yeah.
you've got to do is this. If you're facing this way, you got to go reflect,
Oh.
reflect, and you got to look like a robot. But that's the whole idea of each of those. Did Varun change height when he was doing that? Did the size of his feet change? No, just the direction that he was facing. Everything about him is exactly the same, except for his location or his orientation. He didn't get taller as he was walking. He didn't get shorter as he was walking.
So wait, I have a question.
Yep.
So like, when you're typing about like in a graph, translations is basically saying like, if let's just say in a graph right here, your point is between 3 and 5. You're
Yep.
saying you're reflecting 0 and 4. That means you can actually.
Well, let's do this. We're going to say Varun started here. We're going to redraw what we just watched. I said, Varun, translate 3 steps towards me. This is V prime, or translate 3. Now, that's on the x-axis, left and right. He wasn't floating. He didn't sink into the concrete. So his y-axis didn't change. On a 2-dimensional thing, right? If you're watching this on your monitor. Then I said, Varun, reflect, right? We're going to say that at that time I said turn towards the camera. So he was looking this way.
Hey, am I gonna be in the video?
I'll put you out, don't worry.
Uh,
Unless you want to be in the video.
I'm good.
When I ask Varun to reflect, that means reflect Varun across a line. Right? And now that means he was facing this way towards the camera. After his reflection, he's looking that way. Right?
Yeah.
You always look at yourself in the mirror. Think about that. Yes?
If it's a V, wouldn't the point be facing like this?
Ah, yes, that's not, this is the point V. I'm using his eyes this way. So this is changing the direction of his eyes. What you're saying is if we flip, you want me to actually like flip the poor man's ladder? Let's do this.
No.
Because that's the accurate reflection.
Yeah, but
Oh.
if I said reflect Y, you're not going to show me this answer. You're saying flip the point's name. Now, I'm using the arrows as his direction that he's facing. Yeah. Now, let's do this. We have this to here. Here's Varun Prime, which sounds cool. We'll give him like sunglasses, right?
That's
I know Varun. I don't mean to offend with my bad drawing. Now, wait, no, he needs to be looking dead on, doesn't he? This is Varun looking into the camera.
that is not.
Varun, do you want to draw yourself?
No, I'm good.
Okay, let's change this.
No, I'm good.
Let's go Thimble,
Okay.
Thimble Prime,
Yeah.
Thimble Double Prime. Now,
Oh.
all right, so now I walked across the camera's plane. I'm over here, looking terrified right there. And I looked right into the camera and I realized this is going to be on YouTube for everyone to see. So I have a moment of panic and I reflect myself across an axis in front of me. So now you see my hair, right?
Yeah.
Then I take a moment to collect myself. I start to rotate around. So now we reflected thimble across some line. Now we're going to rotate, ooh, a little longer, 180 degrees around thimble. That means I'm going to be from facing this way
You're gonna face yours to the camera, right?
to the camera.
And it is terrifying.
I'm smiling, but I still feel uncomfortable. I got my eye on where I want to turn back around. So now I'm going to rotate again.
This reminds me of the recording you showed us in the beginning of the school year about dog.
Yes, that's actually where we're not going to do too much on topic one. Back to the hair one. Okay, so all of these, thimble doesn't do anything in size or anything, right? He stays the same. I walked over, had a moment of panic, flipped around and looked at the board, gave myself some words of encouragement. But from this panic state to here, have I changed size? No. So that's a rigid motion. I'm preserved in my sides and my angles. Now, I'm rotating. I'm not going to spin 3 times around like Varun did, being a good sport. I'm not getting taller, I'm not getting shorter. All I'm doing is changing my orientation. That's too many times. All right, now I got to go back to the board. So I did spin 3 times. This is what a rigid motion is. It preserves everything. All right. If I said Varun, spin 5 times, 6 times, 7 times, and he said, I've had enough of this, and he flipped his desk. That's just a rotation of his desk, right?
But I have a question. So
Go ahead.
rigid motions are basically saying like this. If this pen, like you can move it, but it won't like shade. It won't.
Yeah,
Like,
Varun, throw me your pen. All right. Your pin translated, rotated, and reflected over there, right?
Oh yeah.
It's spun through the air, rotated, landed.
Oh, I thought you would have to.
Varun, the joke is always, I never catch anything. I just stand there and let it hit me. You just miss. So, now if I do this, pretend there's no rotation. That can be mapped as a translation. Varun, throw it back to me, but make it rotate a bunch. And then that's going to lead us into our composition of rigid motion. Not for the eyes, I don't have my glasses on today. But make sure it's spinning, throw it to me. And then it rotated towards me, right?
Yeah, I did.
Alright, if we broke your pen, I'll buy you one.
I have a new pencil, so I can.
No, I'm not here to destroy your pencil. So, here. So when Varun threw it, it was rotating. But what else was it doing while it was flying? Translating. How in the world do we represent that?
I bet this YouTube video is about to get a lot of content.
This is, we'll call it Varun's pen, was translated X units and Y units, right? Because we did have an overall change because I didn't catch it. I let it hit the ground. It went from a positive height to 0. And we have to compose that with the rotations. Oh man, you spun that thing pretty quick, right?
What?
The pen.
Oh yeah.
Let's say you had 24,000 degrees of rotation around, well,
24,000. That's like.
24,000 divided by 360. How many is that? Let's find out as many as you think it is.
I think it's like 500.
Something like that, right?
Yeah, no, it's like 1,000. Wait, yeah, no, not wrong. That's. I don't know.
Yeah, it's only 67 turns. That's fair. So, this means that wherever Varun's pen started, its end result, Varun's pen prime, has to be a collection of all of these rotations and the translation together. And that's where your composition of rigid motions comes together. You have to consider all this. I can now take my terrified thimble and look at the map here, the translation, the reflection, all these rotations. Well, 2 rotations of 180 degrees really is just one rotation of 360 around thimble. So I can already scale this down to just be thimble translate xy composed with, wow, this is translate thimble, reflect thimble, rotate 360 around thimble.
Topic. So basically, you have to be really accurate, like just telling, because I remember that when I took this topic 3 test, I had to be so accurate because if I don't do it, the whole thing.
Right, and that's why I'm making this lighthearted, because the next thing we're going to do is going to be so much, I don't want to say soul crush, but it's
Oh, you catch it.
I caught it. Please tell me that's on camera. I've never done that before. Usually I kick it and it hits me in the teeth. Now, what we're saying here is all of this terror can be mapped onto a translation, a reflection, and a rotation. You can add rotations together. We didn't consider whether I was rotating in terror in a positive or negative direction. So my question to you is, if I start here at this point and I rotate this way, is that positive or negative rotation?
That's a negative correlation.
All right, let's do this. Hands up for positive, no hands for negative. So positive is here, negative is here.
It's clockwise or not?
Because
Yes, but which one's which?
X, it's like going this way, and that's all positive.
So the easiest way to remember it, look at the clock. You see the second hand? That's a negative rotation.
Wait, where?
On the clock on the wall, sir.
Oh, there.
The hands on the clock have a negative rotation.
Yeah, I was right there.
You were right. You were half right because you only put half in. But you were halfway there. Yeah. I needed a confirmed commitment. No. Maybe. So here, and the other way to remember it, which quadrant is this on the graph? 1, 2, 3. So this is 1. This is 1 plus 1 plus 1 plus 1. So that's positive as well. I think it's easier, especially during the EOC, to peek back at the clock. The proctor's not going to say anything, and as soon as you see that red hand, you're going to say, okay, that's going in a negative rotation.
Oh my god.
So I'm not going to ask for room to come up, but if he were, let's say that we have a drone and we're looking down.
A drone?
Yeah, and we're filming straight down. Which direction are you rotating, positive or negative?
Wait.
We don't actually have one.
Oh, wait, go down?
Yeah, but this is just saying, here's the top of your head,
Oh.
and you're rotating this way.
We
Would
want
you
it to be negative.
double check that for me? Look here, you're going this way. That's positive
How's that possible?
because the arrow's pointing. Look at the hands of the clock. Is that going the same way as the clock or
Oh,
opposite?
wait, wait. Oh, it's going positive. It's going clockwise.
This is positive,
Oh, it's going counterclockwise. Clockwise is...
which is weird, right? Because counterclockwise is positive, clockwise is negative. Translating is that's getting this.
I guess so.
Right. So the next time you ask when are we
I
going
have something like next to like this rigid motion.
Yep.
Like, what was that? Like when, like, and I have something like, you know, bowling, right? Bowling things. Like when
Yeah.
you roll the ball hits the thing.
Yep.
The pins move around, but the thing
But-
is they don't like change the size.
That's exactly right. Think of bowling. You roll the ball down the lane. If you can hit all 10 pins, they scatter in different directions, orientations. But as the pins change size, that's a rigid motion having.
So all rigid motions are congruent, or they form.
Yes, perfect way to put it. The result of all rigid motions, no matter how many I do, will always be congruent at the end. This marker, if I do this, is still the same size. If I had a way to throw it and stretch it, it would be similar, but not congruent. All rigid motions create congruent shapes at the end, no matter how many you do. Yeah. So I think we covered all that. Now, here's the one thing that I don't like that they don't give you. And I don't know any other way. I don't have a system for you. I don't have a story or a clock that you can look at or anything to help you make sure you always get these right.
All right. How control is going to be with that?
This will drive you crazy.
Yes, it will.
The only thing that I can do.
Oh, it's 22 out of 50.
Say that again?
You're 22 out of 50. That's an achievement.
We're on which one?
We're 22 out of 50.
What's the achievement? Running out of time?
No, we finished 20 pages of work.
Yeah, I got you.
Yeah. Okay, rotation. Oh, I think this isn't that's hard. Because if you're rotating some, wait, no, if you're
Well, let's do it this way. I'll give you a minute to copy it down. I'm going to get a sip of water. Just copy these. I said I don't have a way. I do have something minor that's not a huge element. It's kind of just a little confusing. I think most of us are going to be better off trying to memorize 90 and 270. 180 and 360 are kind of fall out in their common sense with each other.
no. Wait, we have this in our papers.
Oh yeah, well, I'm asking to write it down. Literally the reason I handed you the paper so you didn't have to write anything down. Other than throwing things or saying anything. Alright. The way this is read. It would be nice if we had 0, 0 here, but then we can make it negative. We can't do that.
Wait, I have a question.
Huh.
So like, I haven't you can just substitute the x and y. Like if you can put a plug in 3 and 5.
That's what I'm gonna do. Yep.
Oh,
Yep. So I'm gonna start with this point right here. That's 1, 0. If I rotate it 90 degrees, it's gonna go this direction, and it's gonna land on my next axis because these are perpendicular. That's a 90-degree rotation. Now this is 0, 1. Now the reason I don't like using 1, 0 here, but it is a nice way to start, is whatever my x is, it just goes to my y. And whatever my y is, I move it over and multiply by -1. So we'll do it with another point in a minute, but I want to get through this as quickly, as smoothly as possible the first time. My 180-degree rotation. So start here, hit 90, stop at 180. And I take this and I make both parts negative, but I keep them in the same order.
oh, just basically just putting your value to the other side.
Mm-hmm.
Oh, okay. So if it's like, let's just say if it's like -2 over 6, it will be 2 over 6.
Wait, so -2, 6?
Yeah, and then it'll be 2 over 6.
Let's do that one next. Let's get through the full rotation and then we'll do that one next.
And then 180 over 8.
So now if I take this and I go 270,
That's going to be 2.
my x and y change places again.
So we minus 1 and minus.
Wait, my x and y change places. Let's actually change their places. And then my x goes from positive to negative. So, and that actually is that coordinate. Why did I not include 360? Why did I not include 0?
Wait, I have a question.
Yep.
Wait, that's 180 degrees.
Which one is?
This one we did so far.
Here?
Yeah, shouldn't 270 be there?
So if I go from here to here is 90.
Yeah.
180.
Oh.
Yep. And then if I go 360, I'm just going to end up right back where I was. And if I go 0, I never move, so I'm right where I was. So 0 and 360 have the same values.
Imagine it's a problem. There could be like 45, like 45 degrees. It'll be like half of the way.
45 degrees? We can do that. Would you rather do 45 degrees?
Yeah, I want to see what's 45.
Oh, you mean the math for 45?
Yeah.
Oh, I thought you meant a point 45 degrees off of center. Oh, I have no idea what that would be off the top of my head. But let me do one better for you. Let's do the point 1, 1. That creates a 45 degree angle. So at least I'm giving you some 45, okay? Don't put 1, 1 here. We're going to put it here. If I rotate it 90 degrees room, where is it gonna go?
Wait, I can't see.
From here to here, right?
Oh, yeah.
It's just gonna go in the second quadrant.
Yeah.
Second quadrant is always negative, positive, right? There's no multiplier here, so I'm just gonna take this and make it -1, +1. Does that follow the same steps though?
Yeah.
Yeah, take this over.
Oh, yeah. Just reverse it.
Now, if I wanna go 180 and just negate both.
Okay, cool. And then 270.
270, I start here, I change their order, which I can't do, so we're gonna have to do a third one to show all the examples. And then the x value becomes negative.
Yes.
So that's the 0.11 rotated in all the quadrants. Now let's do a different one.
Yes.
But that doesn't have all the numbers the same. Let's do 2, 3. If I rotate it into the next quadrant in a positive direction, I know that I'm going to have to negate something and do something. This is telling me swap their order. So this becomes 3, 2. And then it says put a negative on the front, or multiply it by -1. And that is a 90-degree rotation.
Do we have to memorize these for the lesson?
Unfortunately, yes. But this is why I kind of wanted to show you, starting with the easiest case, double case, and this, so you can kind of get them on your end. Yes.
Would we ever be asked to rotate it not 90 or negative?
Not in this class. This, yeah, we're just sticking to the cardinal easy ones.
Oh, you need to do it.
Now, don't fall for the trap that you now need to apply the 180 rule to this, right? You can just reapply the 90 rule, or go back to your original point and apply the 180 rule. This is just going to be -2, -3.
I have a question.
Go for it.
In the EOC, will they, in the EOC, it's session 1 and session 2.
Yes.
This will be in session 1, right? These session math will be in session 1.
I don't know which session is which. There's a calculator section and a no calculator section.
This is no.
This should be in the no calculator section. Otherwise, it would be a waste of a question that you don't need a calculator for. Here, if I go back, my x goes into the back-hand side and it becomes negative. And then my y comes out front, and it's positive. And that's how we do rotations.
Will the first quadrant always be positive and then the first quadrant?
That is a really good question. For this example, yes, but no, we can apply these rules. Let's do this. I'm going to change to black.
How do they change the formula then? If the first ones have negatives, then how would it change?
They would actually stay exactly the same. The only difference is, let's do it with this, but let's start in a different quadrant. And the reason this will still work is if you think about it, I have 90 plus 90 is 180 plus 90 plus 90, right? It's going to just keep being multiples of 90. And there's only 4 quadrants, so you're just going to get the same points repeated forever. So if I start at 3, -2, and I want to rotate it 90 degrees, it's going to take me back into quadrant 1, right? But I'm still going to use this rule. Whatever my x was, put it in the back. Whatever my y was, put it out front. And then multiply it by -1. So negative, negative, positive. And look, we're right back where we started. So, another way you can do this is only memorize this one. And then if it says rotate 270, apply this rule 3 times and you'll end up at the same place. Just like here, if I go from here to -3, and I want to go 180, if I apply the 180 rule, I'll just end up right back here, right? Think of this as just how many degrees do you have to walk. What does the arc look like? So your arc measure here is 90 degrees, but if I start here and go to here, it's 180 degrees. If I go this far, it's 270, and if I get back to where I started, I've walked a full circle or a completed arc of 360.
Yes.
Does that help?
Yes.
We just did that without the thing.
Yes, problem 12.
All right, remember everyone gave me the approval to skip those, since we kinda know where we good to skip those, just for sake of time. Alright, topic 12. This is probably the only topic that looks like what we thought geometry was gonna be like.
I have a question.
Yes, sir?
When can I eat like my food?
Anytime you want, there's no limitation. We're gonna sanitize the area before we leave anyway, so you're good.
We're not going somewhere to lunch, but there's not this new work.
I was just gonna sit at my desk and have a snack while you guys ate. Do you want to go, like, leave the room and have a break out of the room? Oh yeah, no, you guys can meet in here anytime.
I thought you said we were going to go to a
Yeah, and then we just move right. Do you guys want like a quick break?
Yeah.
Okay, we'll take a break until, when do you guys want a break? You want the full half hour? You want 15 minutes?
It's supposed to be warm. It's actually
Alright, Shannon's got her head down, we're gonna let you pick. How many minutes do you want?
I guess 10 or 15, right?
We'll go 15.
Yeah.
I'll get my phone number.
So